Hydrogen as a fuel, a lot of energy is evolved during combustion of hydrogen, so it can be used as a fuel. Let's compare it with others. Its heat of combustion is 286 kilojoules per mole, per gram will be 143, per liter will be 12. So hydrogen liquid state will produce around 285 kilojoules per mole and 142 per gram and 998 per liter. LPG is less useful than hydrogen, as can be seen by this data, and same way methane also is less useful as compared to hydrogen. Octane liquid is also least useful. So the best is hydrogen as a fuel because it produces only water as a product, which does not create pollution. LPG, methane, octane all will create pollution. And hydrogen is best in terms of calorific value also. Only problem in its usage is that it is highly combustible, so its storage and transport is slightly difficult. Dihydrogen releases large amount of energy on combustion. On a mass basis, dihydrogen can release more energy than petrol, that is 3 times, and even does not create pollution. Moreover, pollutants in the combustion of dihydrogen will not be there except if there is impurity like methane, then small amount of CO2 and water will be formed. Otherwise, and it is also possible that some oxides of dihydrogen are formed, which may be due to the impurity of dinitrogen present along with hydrogen. Thus, of course, can be minimized by injecting a small amount of water into a cylinder to lower the temperature so that reaction between nitrogen and dioxygen may not take place and pollutants are not produced. Dihydrogen gas is converted into liquid state by cooling to 20 Kelvin. Nowadays it is used in fuel cell for generation of electrical powers. It has been used in Apollo space program. The basic principle of hydrogen economy is the storage and transportation of gaseous and liquid hydrogen. Falling substances are used to make tanks to store hydrogen fuel. Na(NI5), titanium hydride, magnesium hydride, these are used for storing hydrogen. For the first time in India, hydrogen was used as a fuel for auto vehicles in October 2005. For 4-wheeler, 5% hydrogen is mixed with CNG and it is being used as a fuel, and pollution has been reduced to a lot of extent in Delhi. Nowadays, hydrogen is being used in fuel cell for producing electrical energy to large extent. Next topic is hydrides. Dihydrogen under certain conditions combines with almost all the elements except noble gases to form binary compounds. They are called hydrides. It reacts with electropositive metals to form ionic hydrides. For example, magnesium will form magnesium hydride. Boron will react with hydrogen to form P2H6 diborane, which is boron. Dimer of BH3, diborane, we call it, it's boron hydride. These hydrides can be classified into 3 categories: ionic or saline or salt-like hydrides, covalent or molecular hydrides, metallic or non-stoichiometric hydrides. First we take ionic or saline hydride. This is formed only by group 1 and group 2 elements, that is S block elements, which are highly electropositive in character. They are stoichiometric compounds, that is their composition is fixed. However, significant covalent character are found in lighter metal hydrides like lithium hydride, beryllium hydride and magnesium hydride. Reason being, ionization enthalpy of lithium, beryllium and magnesium is quite high. In fact, beryllium hydride and magnesium hydride are polymeric structure because they are Lewis acid, that is their octet is not complete. However, their melts conduct electricity and on electrolysis liberate dihydrogen at anode, which confirms the existence of H negative ion, that is hydride ion. This is 2H negative in the molten state. When electrolyzed, it gives hydrogen at anode, proving the electronegative nature of hydrogen also. Saline hydrides react violently with water producing dihydrogen. It means that these hydrides are basic in nature. Sodium hydride plus water gives sodium hydroxide plus hydrogen gas. Lithium hydride is therefore used in synthesis of other useful hydrides. Lithium hydride is a good reducing agent. It can reduce Al2Cl6, which is dimer of AlCl3, and result in the formation of lithium aluminum hydride, which is popularly used as a reducing agent. Thus 6 lithium chloride is formed. Lithium hydride can form complex hydride with B2H6 LiBH4, lithium borohydride, which can be used as reducing agent. Similarly, sodium hydride can react with B2H6 to form sodium borohydride, which is also used as reducing agent. Why this reaction takes place? Because lithium can easily give hydride ion to BH3, which is electron deficient, and after forming BH4 negative, its octet becomes complete. The thermal stability of hydrides decreases with the increase in size of cation. Lithium hydride is thermally most stable and cesium hydride is thermally least stable because atomic size goes on increasing, therefore thermal stability goes on decreasing. Similarly, calcium hydride, which is called hydrolith, is most stable and barium hydride is least stable. Beryllium hydride and magnesium hydride being covalent exist as polymeric structure. Covalent or molecular hydrides. Most of the non-metals react with hydrogen to form covalent hydrides, especially p-block elements. Familiar examples are methane, SiH4, Saline, ammonia, water, H2S, HF, HCl, HBr, HI. Being covalent, they are volatile compounds, means they have low melting and boiling points, except water, which is permanent liquid, and ammonia also can be liquefied at room temperature. Molecular hydrides are further classified into three categories. First are electron deficient, where the octet of the central metal atom or non-metal is not complete. Electron precise, where octet is complete. Electron rich, where octet is complete along with there is a lone pair of electron. Electron deficient hydride, as the name suggests, has too few electrons, that is less than the octet. Diborane is the example. This acts as Lewis acid, that is electron acceptor. Along with that, BeH2, MgH2 are also electron deficient and Lewis acid. Electron precise compounds have the octet complete, and example is all group 14 hydrides: methane, silane, germane, stannane, and plumbane. They are sp3 hybridized and have tetrahydrogeometry. Group 15 and 16, 17 hydrides have excess of electron after their octet is complete, and these electrons exist as lone pair, and these are electron-rich hydrides. Ammonia has one lone pair, water has two lone pairs, HF has three lone pairs. So they all behave as Lewis bases, that is, they can donate electrons. Let's take up an example. Would you expect the hydrides of nitrogen, oxygen, and fluorine to have lower boiling points than hydride of their subsequent group members? Gives reason. It is correct that we expect that ammonia has highest boiling point among its hydride, not highest, rather it is in the middle because of intermolecular hydrogen bonding. Phosphine has lowest, then is arsine, and then comes ammonia. Water has highest in its group due to intermolecular hydrogen bonding to a lot of extent. HF also has highest in its group because of intermolecular hydrogen bonding. And these are liquids where other hydrides of their members are gases. It is due to high electronegativity of nitrogen, oxygen, and fluorine and their small size and strong hydrogen bonding is responsible for their abnormal behavior. Hence, the boiling point of ammonia, water, and HF will be higher than the hydrides of their substituent group member. Ammonia is not highest, it is in the middle of the group. Metallic or non-stoichiometric or interstitial hydrides. These hydrides are mainly formed by D block and F block elements, or we call them transition metals. The metals of group 7, 8, 9 do not form such hydrides. Even from group 6, only chromium forms this non-stoichiometric hydrides. These hydrides conduct electricity, heat and electricity, though not as efficiently as their parent metal. Unlike saline hydrides, they are almost always non-stoichiometric, that is, their composition is not fixed, being deficient in hydrogen. For example, these are the formula. This is lanthanum hydride, where hydrogen is 2.87. A terbium hydride, hydrogen is 2.55. Titanium hydride, 1.5 to 1.8. Zirconium hydride, 1.3 to 1.75. Vanadium hydride, hydrogen is 0.56. Nickel hydride, hydrogen is 0.6 to 0.7. Palladium hydride, it's 0.6 to 0.8. That is, their composition is not fixed. That's why they are called non-stoichiometric hydrides. Earlier, it was thought that in these hydrides, hydrogen occupies the interstitial in the metal lattice, producing a distortion without change in its type. However, recent studies have shown that except for hydrides of nickel, palladium, cerium, and actinium, other hydrides of this class have lattice different from that of the parent metal, that is, lattice changes. The property of absorption of hydrogen on the transition metals is widely used in their catalytic reduction or hydrogenation reaction for preparation of large number of compounds. Some of the metals like platinum and platinum can accommodate a very large volume of hydrogen. Therefore, they are used as storage media and they are widely used as catalysts. The property has high potential for hydrogen storage and as a source of energy which we need. Hydrogen reacts with transition metals and inner transition metal to form interstitial hydrides. In these hydrides, small atoms occupy some of the holes in metal lattices. These hydrides are non-stoichiometric compound. One example is cerium. Hydrogen is 2.8. All of them give hydrogen easily, therefore they act as strong reducing agents. Can phosphorus with outer electronic configuration 3s2, 3p3 form pH5? Answer is no. Although phosphorus can exhibit +3 and +5 oxidation state, +5 oxidation state is shown with oxygen, chlorine and fluorine, where it has which are good oxidizing agent. With hydrogen, it cannot show +5 oxidation state because firstly, hydrogen has high bond dissociation energy, 436 kilojoules per mole. Also, electron gain enthalpy value of hydrogen also is low and it does not favor the highest oxidation state of phosphorus. Therefore, phosphorus can only form pH 3 and not pH 5.